In this lesson, we'll talk about global maxima and minima. We've already talked about the concept of local maxima and minima, in which you're looking for points that are the highest and the lowest in some small region. Now what we want to do is look at a global maximum and a global minimum. This is a maximum that occurs among all the points, and a global minimum would be a place where you're looking from all the points and find a smallest one. It is very possible for a given function that if you're just looking at some open interval on the function, perhaps even the whole real number line, it's very possible that you do not have a global max or a global min. So let's look at this particular picture first. This point, as you can see in a small area, is the smallest point. We would call that a local minimum. And then this point we would call a local maximum. But if you look around elsewhere in the curve, you've got points up here that are higher than that local max, and you've got points down here that are lower than that local min. However, this point right here, another local min, you'll notice that this has the lowest point of anywhere on the function. That's what makes it a global min. Also, if you look at this graph, it seems to just be shooting off to infinity on both sides, which means that there's actually no global maximum, because it never reaches any sort of highest point on the whole interval. However, there is a place where we can always find a global max and a global min. Sometimes this is called the extreme value theorem. If you have a continuous function defined on a closed interval, this is where we say a less than or equal to x, less than or equal to b. So we're including the endpoints a and b. If you have a continuous function, simply saying you can do this without picking up your pencil, then you will always have a global max and a global min on that particular interval. And so what we'll have to do is figure out, how do we find these things? Well, according to this theorem, it actually will always appear in only a few possible locations. Your local max could be your global max. A local min could be your global min, or the global max and global min could show up at the endpoints. So notice the global max for this one shows up at the endpoint, whereas the global min for this one shows up at one of the local mins. So we're getting closer. How do we find these things? Here's the idea. We know that the critical points will help us find all the possible local maxima and local minima. So if we start by finding the critical points, then what we can do is just check the critical points and the endpoints. Now when I say check, I actually don't care whether these are a local max or a local min. I don't actually need to know that it's a local max or local min. I'm just wanting to know, is it the highest point on the whole function or the lowest point on the whole function? What this means is I'm just going to look at the y values. The original function gives me the y values, so I'll take the critical points and the endpoints and plug them into the original function. This means that I don't have to do as much with the derivative, but keep in mind when I say critical points, that's what you get when you take the derivative and set it equal to 0. However, once you find those points, you'll just simply take the critical points and the endpoints and plug them into the function. The highest value is where the global maximum occurs. The lowest value is where the global minimum occurs. So let's take a look at this example. For this problem, if we want to find the global maximum and global minimum, what we'll do is we'll take a look at this interval from -7 to 13, and notice that our critical points of -3 and 7 are within that interval. Again, all I have to do is check the critical points and the endpoints in order to do this. So I'm going to calculate f of -7, that's one of my endpoints, f of -3, f of 7, and f of 13. And then let's just plug these in. Again, this is the original function because I'm looking at the y values. I'll get -7 cubed minus 6 times -7 squared minus 63 times -7 plus 10. This is the original function. And let's see what we get out of this. I get -186 for this one. Similarly, for -3, I get 118. For 7, I get -382. And for 13, I get 374. So now all I have to do is look at these 4 points and figure out which one is the highest and which one is the lowest. It looks like the highest one was the 374. The way that I would normally word this is global maximum of 374 at x equals 13. Notice that this is at one of the endpoints. Well, now let's look for the smallest value. The smallest value is the negative 382. So what I would write here is global minimum of negative 382 at x equals 7. This problem right here is a great example to finish off the 5-fold question that I mentioned in class, where you have increasing and decreasing as one question, local max, local min is another question, and then global max and global min would probably be wise to do as a third question. The fourth question would be the concave up and concave down, and the fifth question would be the inflection points. One more example. We've got the rate at which photosynthesis takes place in the leaf of a plant given by this expression. We want to know when the photosynthesis is occurring fastest and at what rate. Now the graph is sort of giving away some of this information, but we can find it. So what we want to do is figure out, again this being a rate here, you don't really have to think about it too much with derivatives, just know that this function is telling us the rate already. And so if we want to know where it's occurring fastest, we can simply look at the graph and say, well, it's occurring fastest where the derivative is 0 here, so we'll take the derivative, set it equal to 0, and see what we get. I'd imagine it'll be this 20.12 in the graph, but we should know how to do this numerically as well. Let's take the derivative. The 100 is just a constant. I'll leave it in front. And then we've got an e to the kt here. That's going to give me k e to the kt. And then I have another one. Looks like I'm going to end up with a plus 0.1 e to the negative 0.1 t. That gives us our derivative, so let's set it equal to 0. Well, if I set it equal to 0, the first thing I might do is go ahead and distribute the 100 to get negative 2 e to the negative 0.02 t plus 10 e to the negative 0.1 t. Now the technique to solve this equation from here is a little bit different from what you may be used to. What I'm going to do is multiply both sides by e to the 0.1 t. The reason for doing this is I'm trying to knock out the negative exponents. So by doing 0.1 t, you'll notice that's the larger of these two values, and that's very beneficial to us because then we'll be able to deal with positive powers. In addition, it will also make it so that only one e appears. I get negative 2 e to the, when I add my exponents, I get 0.08 t, and then I just have 10. And on the right side, 0 times anything is 0. Now I can go ahead and start solving this. I get negative 2 e to the 0.08 t is negative 10. Divide by negative 2 to get e to the 0.08 t is 5. Take the natural log to see 0.08 t is the natural log of 5. Keeping in mind the log here would cancel with the e. And then finally divide by 0.08 t, or just the 0.08, and this gives us our answer, which is about 20.12 as we expected. Notice that since this is a t value, this would be in days. So after 20.12 days, photosynthesis is occurring fastest, and to find the rate of that, we would simply do p of 20.12, which if you plug that into the function, you should get 53.5. There's no particular units on that number, so we'll leave it as is.